So now anything in real life that repeats itself in a cycle, we can write a sine or a cosine graph to model it. All you need is a maximum point and a minimum point, and that's enough, if it repeats itself on a cycle, to draw the whole graph. So in these word problems, this will be the easiest question because, look at this, they gave you the equation already. So what we're going to do, I'm going to erase this part here, is we're going to sketch the graph, and we can sketch the graph using, see, just what we did yesterday. Hopefully yesterday was really helpful for practicing and getting to understand how to graph. So if I was graphing this, the first thing I would look at before I even start my scale is my D value is 13.7 and my A value is 4.5. So in drawing my scale, I can put 13.7. I'll choose a spot for that. How about right there? That's my center line. And my amplitude is 4.5, so that means I'm going to go up to a maximum of 18.2 and down to a minimum of 9.2. And I try to make my scale somewhat appropriate, estimating how much 4.5 is. So this actually completed the G value, and we did the amplitude to find our maximum and our min. Next, we have to find our period, and our period is always 2 pi divided by our B value. So we go to our calculator and figure that out, and we get 12.5. So since our period is 12.5, we pick some spot on our x-axis to label 12.5, divide that into 4 equal sections. Half of 12.5, 6.25, half of that, 3.125, 3 times 3.125, 9.375. Label all 4 sections. And we're done with the value. Next, we would draw a dotted line before the shift, but can you see in this equation, there is no shift. So we don't even have to worry about drawing it. Well, you could draw dotted and then realize there's no shift and then draw a solid line afterwards. That would be fine. But it is a negative cos graph, which means it starts at the minimum. Then it goes to the center line, then to a maximum, back to the center line, down to a minimum. And here is our graph. Part B says that a bulk carrier needs 14.5 meters of water to dock safely. Okay, so lots of English here. This is just fancy word for a big ship. And the tides go in and out, so the water gets deep and gets shallow. And at certain times, if it's shallow, the ship is going to hit the ground. So in order to be at the dock, inside, parked safely, it has to have enough water. If we look at our diagram, I can label 14.5 on here. And it's only going to be safe from this point to this point. This highlighted section right here is when the water is deep enough. Any other time, the ship's going to get stuck and have to sit there until more water comes in to get propped up again. So I'm going to show you 2 ways to solve this. One requires a graphing calculator or graphing technology, which, if you're also taking an applied course, will be super helpful. Also would be super helpful if you're planning on taking the AP course next year, because we need to know how to use our graphing calculators to solve things in the AP course as well. So, first, we'll solve this with a graphing calculator. If you have a graphing calculator, take it out. And first thing, we're dealing in radians, so we want to make sure that our calculator's in radians. And if we want to graph this, we go to y equals, and we type it in. So it was negative 4.5 cos 0.16 pi. It had a theta. We're going to use x plus 13.7. Just double check if I typed that in right. Yes. Next, if you hit the graph button, most likely this is what you're going to see. If you hit your graph button, you just see a little tiny bit. Because what happens on the graphing calculator is normally it shows you from minus 10 to 10 and minus 10 to 10. That's the window that you get to see. So it's basically showing me up to 10, which would be about here, over to 10 down here, over and up. Like, that's what I'm looking at on my screen. But I want to see all of the graph. So I want to move this window so it looks more like this, so I can see all of it. So to do that on your graphing calculator, first of all, it's important that we graph it by hand first, because we know what we want to see. Do you see that you want to see past 18.2 on the y? And I want to see past 12.5 on my x. So what I'm going to do on my calculator is there's a place called the window, which is what we see. And right now it's going from minus 10 to 10 on the x's. I like to keep a little bit of minus so I can see the axes. So I might go minus 10, but along here I want to see 12.5. So if I go to 15, that would be enough to see the 12.5. For my y minimum, again, I'm going to start at -1 to make sure I still see my axes. But we wanted to go up to 18.2, so I'm going to make my maximum at 20. If you really want even these ticky marks to be at the same spot, that's what the scale does. So I can change my x scale to be 3.125. Then it will mark 3.125, 6.25, 9.375, 12.5, exactly like that. I can't really put in my scales going by 1, maybe I go by 5s on my x. And now when I go graph, I see my graph. It has the ticky marks exactly where I had them down here. It's going by 5s here, 5, 10, 15, 20, and adds that in. So first of all, how to use a graphing calculator so you can see what you want. Next, I'm going to go to y equals, and in y2, I'm going to put that 14.5 in. That's going to draw a straight line across at 14.5. If you don't have a graphing calculator, then this is a great app that allows you to see this as well. You get the app Desmos, then you could graph this, you could graph the straight line as well. And what's really nice about Desmos is it's more intuitive than the graphing calculator. If you want to find out where they intersect, you just put your cursor right there and hit the button and it goes like, here it is. With the graphing calculator, to find out where they intersect, we have to go to a menu that does calculations. So above the trace button is all the calculations you can do with graphs. So if I go second, trace, what would I like to calculate? This time I'm interested in where they intersect, number 5. So I go down to number 5 or hit the number 5, push enter, and it says, what's your first curve? Sure, the blue one, enter. What's your second curve? It automatically went to the second one. Sometimes you can get crazy and have 4 or 5 graphs going, so then it would make a difference. But we only have the 2, push enter. It asks you to guess. I don't know why. Just push enter again. I think it intersects here. Like, okay. Hey, I guessed right, but now it tells me the number. The number is at 9.02 and 14.5. So I can go back to my graph, and I can go down from this point, and I know that it's at 9.02. I also want to find out this one. Where does this one intersect? So I go back to my graph, and I go second, calculate again. Oops. Second, calculate again. Number 5, intersect. Now, if I just push enter on the first curve, because I'm on the blue one, enter on the second curve, we'll go to the red one, it'll always find the nearest intersection point. So it'll find the same one again. So I will have to use my cursor here to move to the left. Oops. There we go. Until I get closer to the one I want to find. Technically, I could have stopped a while ago because I was close. Now I can push enter on the first curve, enter on the second curve, and guess, there it is at 3.48. Question was, for how many hours? So we take the 9.02 minus the 3.48, and we will get 5.54 hours. Using technology is a great way to solve this. This is what an applied math course would have this same question, and this is what you'd be expected to do. Use your graphing calculator to solve it. If you go on to university, or if you're in pre-calculus, we also need to know, how do we solve this? If we only were allowed a scientific calculator, or we were only allowed a graphing calculator, but weren't allowed to use the graphing buttons. How could we do that? So I'm not going to give you enough time to write this down. I just want you to watch. Okay? If you want to write it down later, it'll be on the video. So, and I'll do it fast. I'll explain it nicely, but I'll do it fast enough that you try to write it down, you're going to get frustrated, and then you won't be able to write it down, and you won't be listening because you'll be writing down so much, so it will not work out well for you. So if you really want to write it down, watch the video after and copy it there. Okay, so this is what we want to find. We want to find where these 2 points are. We know that the depth is 14.5. So what we do, or what we can do, is plug in 14.5 for the y value, because we know that. Now we want to solve for t. So what does that mean? Well, we have to get t by itself. So first of all, I'm going to get the cos by itself. Well, how would I do that? I move the 13.7 over, I divide by negative 4.5, and that would get my cos by itself. Now this is a little bit ugly inside. If this was just cos theta, wouldn't it be easier? Because then you know how to solve cos theta questions. You do cos inverse of both sides. So one of the things you can do in math, when things get a little ugly looking, we can just do a little substitution. Why don't we just let theta equal this whole thing on the inside? Because if we do that, not enough time. If we do that, this just looks like this. And how do I solve for theta? Well, I'm going to have to use my cast rule, find my reference angle. How do I find a reference angle? I do cos inverse of the positive value. I get a reference angle. I use my cast rule since cos is negative, and look in quadrant 2, which you would do pi minus your reference angle, and I would look in quadrant 3, and do pi plus my reference angle. So now I have answers for theta. Theta is 1.74, and theta is 4.53. But we're not trying to solve for theta, we wanted to solve for t. But we know that theta equals this. So now we use theta just temporarily to make our life a little bit easier. And now we can substitute back. Now I substitute back the 0.16 pi t for the 1.74. I divide, and I get the 3.48, same as we got with our calculator. I do the same thing with the angle in quadrant 3. And I get the 9.02, same as my calculator. A little bit more involved. Generally, on your exam, normally they wouldn't have ones that are this involved, okay? But then once you get to AP Calculus and Calculus, they kind of assume you can do it. So sometimes that happens from one grade to the next. They're like, oh, we won't test you on the hardest ones, but as soon as you move to the next grade, they're like, well, you did that already, so we expect you to be able to do it and the hardest ones for the next year. So I wanted to show it to you so that you could see it, so that it's going to be expected that you could do this kind of algebra in university or in the AP class. But we get the same answer in the end of 5.54 hours. Okay, now we'll write down again, we'll look at the next question. Does everyone know what a Ferris wheel is? We go to an amusement park, we can draw a picture of it. Oh, I'm gonna make my tower. I gotta move my tower down a bit. There's the center. We've got a wheel. There it is. Perfect. Obviously, it would be connected somehow. And then it has chairs. Oh, so much fun. And you go around and around and around. And are they scary? No, usually not. Only if you're scared of heights, right? And on the very top, you're very high up. If you're scared of heights, it's kind of a little scary. Because eventually they'll stop it to let somebody else on when you're right at the top. So there you are, super happy. There you are, super happy, sitting on your chair, going around and around and around. And because you go around and around and around, it doesn't go too far off. It's cyclical, so we can model this and find an equation with sine or cosine. We just have to think about DAB-C. So one of the things we can do in a situation like this is right beside, we can draw a graph. And I might, the circle's almost too high. Maybe I can move my notes. There we go. Now, normally you come along and you would get on at the bottom, right? Does it make sense that you would start here? And that starting point is a little bit off the ground because it's not very much fun to have a Ferris wheel that hits the ground. It's dangerous. So it says in the question that passengers start at the bottom, which is 1 meter off the ground. Are you okay that I label a 1 there? Now you're going to go all the way around, and you're eventually going to be at the very top. How high above the ground would you be if you were at the very top? So we need to label how high above the ground this is. Okay? And it's not 30.
31.
It's 31. Why is it 31? Well, the radius is 15, right? Does it make sense that this is 15? Then this would be, the diameter would be at 30 because it's 15 twice. But we started 1 meter off the ground, so now we're at 31 meters at the top. And if you know that 31 is the top, you probably also could label your center line. where's your center line going to be? At 16. So the radius is going to be your amplitude. And we can use that radius to find the center line. It's going to be at 16. Now, it rotates once every 20 seconds. So we can go here. Does it make sense if you started at the bottom, 20 seconds later you'd be at the bottom again? That's one period. So when we graph things with DAB-C, we always split this up into 4 equal sections. So this would be 10, 5, and 15. And if it takes 20 seconds to get all the way around, does it make sense that it would take 10 seconds to get right up here? And we've basically got our graph. At 5 seconds, you're going to be, right? 5 seconds, you'd be there. 15 seconds, we'd be over here. So a little bit more difficult question because you have to take the information that's given and draw the graph. Once you've drawn the graph, now you can think about DAB-C. The D value is 16. The amplitude is 15. The B value, right, is related to your period. And we can see from the graph that our period is 20, so our B value is going to be 2 pi divided by 20. And you could reduce that to pi over 10, but I kind of like it as 2 pi over 20, because then the period shows up in my formula. So you don't have to reduce that fraction, but you can if you want to. So as a result, we can draw, or we can write a whole bunch of equations. Does it ask for sine or cosine, or does it say just graph the function and find its equation? So we can find either a sine equation or a cosine equation. I'll do 2 of them. I'll do one in sine and one in cosine. So if I was doing sine, my A value is 15. Sine. B value is 2 pi over 20. Rated in factored form, and my D value is 16. I'll color code this. Where does a sine graph normally start? Sine graph normally starts in the middle going up. Well, the middle going up is now 5 units to the right. So I would show that by having -5. For a cosine graph, A value is the same, B value is the same. So the DAB part, the D value is the same. What changes is your starting point. Where does a cos graph normally start? Right here at a maximum. That maximum is 10 to the right. So I could write -10. Both of those are right. But if I had to pick the favorite equation that a mathematician would pick, they wouldn't pick either of those two. Which one do you think would be the favorite equation that a mathematician would pick? They like the negative cos graph. Can you see why? They like the negative cos graph because it has no shift. It already starts at the bottom, so it makes sense to use that one at the bottom. So our DAB-C practice for graphing also helps us work backwards in word problems to find equations. And again, the DAB part stays the same, whether you're using sine or cosine, positive or negative graphs. Only thing that changes is the starting point. So you choose one of them and find its starting point. So for example, when we chose sine, we said, well, sine normally starts in the middle going up. To have the middle going up, I would have to shift something 5 to the right. So I show that shift by doing -5. For the cos graph, 10 to the right. And for the negative coast graph, it already starts at the minimum, so then it would have no shift, which is kind of nice as a graph. Now part B, estimate the height after 22 seconds. This word is nice for us because we don't have to use a calculator, and as long as our educated guess is close, you'll be fine. So if I go to my calculator, I go to my graph that I did, and I see where would 22 seconds be. 22 seconds would be right about, well, maybe about here. 22 seconds, 21 there, and that's just, oh my goodness. That's messy. This would be 5, 2 would be about there. And then I would go up to my graph and I'd say, all right, about there. I would go over and I'd take a guess. So anything that was reasonable guess based on this would be fine for an estimate. Okay, so when I go to my estimate, about, what is it? Sorry? 2? 3? Well, I think it's higher than 2.
Excuse me, Huskies, can we get the student council executive, please, so the groups representing the grades come to the office at lunch hour for just a very brief meeting? That's the executive from student council at lunch. Come down to the office. Thank you.
If I wanted to find it exact, I could put one, excuse me. I could put one of my equations in. I'll use the negative coast graph because I didn't have to write as much. I could set up my window so that I can see it. This time I need to go past 22 if I want to see 22. And my scale for x's are going by 5s. We went up to 31, so I'll go up to 35. Here's my roller coaster. And I want to find out at 22 seconds, so I'm going to calculate something. This time I'm calculating the value. I'm calculating the value when x is 22. What is y? 3.86. So we were pretty close. So we could use our calculator to find it exactly. So this question, a little bit more difficult because you're just given the situation. And the situation allowed us to find our maximum, our minimum, our period, our center line, and then we could go dab C from there. The least amount of information they would need, estimate what time you'll be 20 meters above the ground. So we could go here. We could draw in 20 meters, so this is 16, I would put 20 would be above there. Go across, there's one point, there's another point. I would estimate at 7 seconds, or at, what does that look like? 7 seconds or 13 seconds. Okay, if you wanted to find it exactly, you'd have to go to y equals in the second one. Is it, what number did they want me to check? 20? 20, I type in 20, that draws that straight line, and then I calculate where they intersect. Enter, enter, enter. 14.14. I want to find the other one. Do it again. But now, I need to be closer to the other one. Just go over that a little bit. That should be enough. Enter, enter, enter. 5.85. 5.85, 5.86. Is it seconds? Is this a realistic Ferris wheel? Or is it a little fast? 20 seconds to go around. I think that would be pretty exciting. I mean, That might be a little bit faster than normal. We could have fun with units on this question. Like, you want a near-death experience, you just put a K here. Can you imagine a 15-kilometer, now you're at the very top, you're 30 kilometers above the ground. I think you'd probably disintegrate if it only took 20 seconds to go all the way around. You could actually, if we wanted to, we could have fun with this math. We could figure out the circumference and find out the distance you traveled in 20 seconds and find out with conversions the actual speed you were going if this was a 15 kilometers and took 20 seconds, right? That would be crazy, right? You could also make this the worst Ferris wheel you ever were on in your life. 20 hours, almost a full day to get one revolution. Oh. That would be a terribly long Ferris wheel.